So thank you, Roman, for that kind introduction. It's a pleasure to be here in Lausanne. I last visited 10 years ago, I think, so it's really nice to be back. I'm told that the audience is quite a general one, so I'm going to give a little bit of history first and background, and then we'll get into the more recent stuff later in the talk. So why is it interesting to capture light on the nanoscale? Well, you might want to look at very small objects. Biology is just beginning when the resolution of a conventional microscope gives up. So if you want to see inside a living cell, then you have to do better than an ordinary microscope. And there are various ways of doing this, which are all rather complex, and some of which have won the Nobel Prize a few years ago. And that's a really important aspect of nanolight, to be able to see smaller than the wavelength of light. Of course, the microscope is the biologist's tool of choice, and they're very, very frustrated that they can't see the things that they're interested in now through an ordinary microscope. Electronic circuits for laptops and iPhones, they're already way sub wavelength. I think 10 nanometers or 5 nanometers is the latest in the writing resolution. And if you want to look them with light, you've got to go sub wavelength. Single molecule sensing. If you can only focus light to something like half the wavelength, which conventionally is the rule, then that's a lot bigger than a molecule. And to trying to get a photon to collide with an electron, which is localized to about a nanometer on the atom, is a conversation between a mouse and an elephant. But if you could squash the photon down to the nanometer scale, then you could have one photon exciting one electron, single molecule sensitivity. To make light interact, to make optical switches, this requires a very high energy density, and you can either do that by taking a fiber, as I've seen this morning in some experiments, and letting the light interact over a very, very long distance, or you can squash the light, focus it into a very, very small cross-section. So if you can only focus light to, say, a square micron, then that's a certain density. But if you can focus it to a square nanometer, that's 1,000,000 times more intense, and therefore you need less power to create a given energy density. And it's the energy density that determines the non-linearity. And more exotic things, time reverse of light. You can force light to retrace its steps, but this again requires high powers. And the problem is, as I've already alluded to, that Abe showed us that with conventional microscopes, there's a limit of about the half wavelength of light, a bit less maybe, to what you can see through an ordinary microscope. And to solve that problem, we have to draw on quite a few things which have been developed in the past. Conventionally, we use Snell's law, or Descartes' law, depending on which country you happen to be at the time. He, and along with several others at the same time, showed how light changes directions in space. And although we now know that light is controlled by Maxwell's equations and is a wave and has polarization and all that sort of thing, Descartes' law is nevertheless is still used to design lenses. And the reason for that is that Maxwell's equations, it's not immediately obvious how light would behave within space just staring at Maxwell's equations, whereas Snell's law gives you an intuitive, if inaccurate, answer straight away, and can be used to think yourself through a problem and imagine new solutions. And we'll have something to say about how to replace Descartes' law with something more precise. Another guy who had something to say about light was, and something to say about space, was Einstein. And in his general theory, he came up with the notion that space is just another material like glass or water or what have you, with some properties. And these properties can be changed by altering the density of space. So if you're near a strongly gravitating object, the gravity changes the metric of the space. If you like, it compresses the space a bit. It does things for the time dimension as well. And that means that starlight traveling near the sun is deflected. So the star appears to be in a different place in the sky from where you'd expect it to be if the light traveled in a straight line. And that was an experiment which Arthur Eddington did in 1919 and was published in the Times newspaper. It's so important. And it confirmed Eddington's general theory of, Einstein's theory of general relativity. More recently, we have evidence of that from the Hubble. So here's gravitational lensing. There's a red galaxy here, a very, very massive one in the foreground. And behind it, there's a blue galaxy. And the light from the blue galaxy is being guided around, a bit like the cloak, really, guided around the red galaxy so that it makes this ring here. So another example of gravity acting on space to make it into a lens. Now this is the conventional bending of light. When light enters the medium, it bends towards the normal depending on the refractive index. When it exits, the reverse, of course. But there's another sort of material which was postulated many years ago now, 50 years ago, I think, which is a material where the refractive index is not positive but negative. So instead of the light bending towards the normal here, it actually bends to the wrong side of the normal. I've got a little sketch of that here. So this is negative refraction in action. The light comes in, and instead of coming this side of the normal, which would be positive refraction, if this angle is negative, that counts as negative, then by this Snell's law, you find you have a material with a negative refractive index. Now, you might say, negative schmegative, we can even do complex numbers. What's the big deal in a negative sign? And you say that at your peril, because negative refraction has many subtleties to it that many very clever people have misunderstood. And I've had long and intense arguments over the years. And it's always come out that negative refraction is beaten one way or another. But right at the beginning, you can see that there's something rather curious about negative refraction, because what I've drawn here is a ray picture. So if I have a Gaussian beam that comes in and it's negatively refracted, this is where the energy goes. But there's a very, very strong law in physics which says if you have a flat surface which is translationally invariant, then there's a conserved quantity corresponding to that invariance, which is mathematically derived from group theory. And the conserved quantity is the momentum of the light parallel to the surface. Now, if this beam's headed in vacuum, say, then its wave vector, its momentum, if you like, points in this direction, parallel to this guy. And therefore, the component along the surface points in this direction. Now, if I said the same thing for this light here, that if its momentum were to point in this direction here, it would be pointing in the opposite direction, and you can never match something in this direction with that direction. That's impossible. And therefore, you're forced to the conclusion that in a negative refractive medium, in order to satisfy very, very stringent laws, the momentum of the light, the wave vector, has to point in the opposite direction from the group velocity, which is where the ray goes. And so you have this very curious situation of which defines negative refraction. The group and the wave velocities are in opposite directions. And to just sort of draw your attention to that with a sketch here, if you have a pulse of light moving through a negatively refractive medium, then the pulse will travel in this side. But if you look inside the pulse these little waves will be trying to get out of the back of the pulse and heading in the opposite direction to the pulse. Very, very strange. It never happens in ordinary light, that the wave velocity is in the opposite direction, but there are some other media. I believe surface waves have a region where they have this strange negative refraction effect of the waves heading in the opposite direction from the group. Now, another ingredient here is how do we think about, how do we control, how do we design materials which have to operate on the nanoscale, because Snell won't hack it, because Snell assumes that you it thinks about light as particles, little pulses if you like, and you can't make those little pulses smaller than the wave, much smaller than the wavelength. So once you sub-wavelength, I'm afraid Snell is out of the window. So you have to think of something else. And for that something, we turn to the ideas that Einstein had, which is that you can compress and stretch and distort space. And that's where transformation optics comes in, which is something which I got involved in quite a long time, actually, but didn't realize its full significance until, well, 20 years later, almost. No, 10 years later. And the idea is that suppose now, Snell works with rays of light, but Maxwell's equations also work with something which can be drawn in terms of lines. And Maxwell works in terms of electric and magnetic field lines. And you can think of those field lines as a replacement for rays. So where the field lines go tells you where the fields are going, and how dense the field lines are tells you how intense the field is. And if you can find a way of manipulating the field lines, then that's a way of controlling the light and also giving yourself a picture of what you're doing through the light at the same time. Now, if you distort space somehow with a very massive star or something, you start pulling it around, then you will also pull these field lines as if they're stuck into a rubber sheet which you're distorting. So if you distort the rubber sheet, you will pull the field lines with it as well. And then, having distorted this sheet how you want, got the field lines to go where you want them to do, then you can turn to a formula which emerged from Einstein's general relativity theory and say, what values of epsilon mu must I use that these field lines obey Maxwell's equations in the new coordinate system? Maxwell's equations have this lovely property that they have the same form in any coordinate system, and the only thing that changes, the things that change are epsilon and mu. And here are the new epsilon mu's in terms of the first derivative of the coordinate system, which must exist for this idea to work. So you must have a continuous transformation. You can't snap these lines anywhere. They were continuous. Well, you may say, well, that's worse than Maxwell's equations, because I don't like the lambdas and things. So, okay, you can handle that. So let's ask for something really simple. I'm going to compress space, the simplest distortion of space. I'm going to compress space like this. And then I'm going to ask, what do I have to do to epsilon mu so that a ray of light going here, so the pointing vector is another conserved quantity which can be represented by rays. So this is a pointing vector, let's say. And if I compress this region here, then the pointing vector is going to do a zigzag. And so what must happen to epsilon mu for this to happen? And it's very easy to find out what values of epsilon and mu, and they must change in the same way, does that. So the answer is this. If you compress space like this, epsilon and mu perpendicular to the compression increase by the inverse of the compression factor. Epsilon and mu in the direction of squashing decreases again by the compression factor. And a nice special case of that is a conformal transformation in which you distort this way, in which you distort that way. And if you do that, compress increase, decrease, compress, decrease, increase, and you get back to where you stopped off. And that accounts for the whole history of conformal transformations, which is closely related, but is a special case of transformation optics. So in the previous slide, I could crawl over this guy here, and I could measure how much has been squashed in this direction, that direction, and the other direction, and how much it had been twisted, and I could tell you what the permittivity and the permeability tensors were at each point here, just using a ruler and a protractor. Now, I'll show you some instances of how we can use transformation optics to understand some very strange things. One of the other things that Largo did 50 years ago, and we had a celebration of a great man's achievement last September, I think it was, in Finland, and he was supposed to be there, but sadly, Victor was in hospital, and he died shortly afterwards, after a long and largely happy life, I gather. So this is one of the things he showed you could do with his negatively refractive material. And what he showed is to get negative refraction, you have to have both epsilon and mu negative. Here I've shown them equally negative and -1. And if you have a negative medium, then you get this negative refraction here, and light bends back towards the axis. And if it does that, it will naturally come to a focus here. And what's more, if you ask what happens downstream, you get a similar effect, and it comes to a second focus here. So you get two foci for your money, and this is known as the Veselago lens. Great curiosity, you can actually focus something which isn't lenticular, it's flat, but nevertheless brings things to a focus. And there the thing sat for many years, and then when I got interested in negative refraction in the 1990s, in 2000, I found myself with nothing to do before lunch one Sunday morning, which is an unusual thing. And I thought, well, what about this lens? Does it obey Abbe's limit? And there was some reason I suspected that it wouldn't do, because in many ways the Veselago lens is unusually perfect. We know that it has, other than chromatic aberration, it need have no other aberrations whatsoever. And so I asked the question, what limits the resolution of this lens? And I did some calculations, and to my astonishment, I came up with the result that the lens, if you design it in the right sort of way, has unlimited resolution. And I wrote a paper called The Perfect Lens, which hellfire fury descended on my head at that point, but has stood the test of time. And I did the derivation algebraically, but it's a simple geometric derivation, which is only the cubic root of that proof of that perfection of that lens. Remember that transformation optics is exact at the level of Maxwell's equations. So if you can prove something using transformation optics, the theorem is exact. So I'm going to take some material, which is just empty space as a material, and I'm going to make a piece of negative refraction out of it. I'm going to do it in this way. So I compress the space, and as I compress, you increase and you decrease. And as you compress more, you increase and you decrease a lot. And then when you compress infinitely so, you go up through infinity, and what happens the other side? So 1 upon x, plus infinity, minus infinity. What happens to x as it goes through 0? It goes plus x and then minus x. So you merge the other side of this infinite compression with a negative value, okay, of both epsilon and mu. So now, by making a space which is compressed, is convoluted like that, and that's a very, very weird space. You see, what's funny about that space? It has 3 manifolds. So it exists on 3 surfaces. Okay. So when the light encounters this negative material, you think it's doing this and this. But what the light thinks it's doing is going around this manifold here. So the light passes this point once, twice, and 3 times. And what is reproduced here at the level of Maxwell's equations, if you've done all this stuff right, is exactly what was here. Okay? So that's a geometric proof that the lens is perfect if you could make something which has a negative refractive index, which is exactly -1. And that's the key. These negative quantities are the key to making controlling light on a sub-wavelength scale. There's some sort of hilarious consequences to this. So you might think that it will be amusing to fill your swimming pool with a material with a negative refractive index, and then this little ray tracing diagram shows you that anything is in the pool at this depth here, to an outside observer, you would think the fish were swimming in thin air, and the other amusing things you can construct out of negative refracting medium. I leave you to entertain yourselves with that in the future. So here's my favorite set of quadrants. This material here, when epsilon and mu are positive, that's glass and water and so on. If you make epsilon negative, epsilon is negative in metals like silver and gold, in all metals in fact, and it results in an imaginary refractive index because the refractive index is the square root of epsilon times mu. If one of them is negative, then the refractive index is imaginary, and that means it's opaque. More rarely occurring are materials with mu less than 0, but never in nature do we find anything when both epsilon and mu are negative. And if that is the case, refractive index ceases to be imaginary, it becomes real again, but it becomes less than 1. You can show with a bit of algebra that it has to be less than 1 if both epsilon and mu are less than 0, less than 0 if both of these are less than 0. And that was achieved with metamaterials, but I don't want to talk about metamaterials today. Instead, I want to move on to the optical analog. And when I wrote my paper, I knew that the greatest interest in this will be in the optical reason. And there's actually a let out you can get, because although at optical frequencies, you can have metals like silver and gold with a negative epsilon, it's hard to find anything with a magnetic response optical frequencies anyway, and finding something with mu less than 1 is almost impossible in nature. So I had a get out clause, and it's this, that let's make the following observation about light. The light it's been described as a dance between electric and magnetic fields. And if you start with an electric field, over time and over space, the electric field mutates into a magnetic field, goes back to an electric field, and so on and so forth. Now, you know this very well, I'm sure. But if you're interested in nanotechnology, and you're interested in nanotechnology on a nanoscale, so everything's nano, and the light starts off as an electric field, it never has chance to acquire a magnetic component because it doesn't go far enough, okay? And if you don't have a magnetic field, then you don't care what mu does. So if you're content to make a really, really small lens that only operates on the nanoscale, that's enough. And I was taken up on that by the Berkeley group of Zhang Tang. And way back, they made this system here. So this is what they're looking at. It's a chromium layer on quartz, which is patterned on a 50 nanoscale, 50 nanometer scale. This is a spacer layer, and here's a piece of negative epsilon material, which is silver. So it's an odd thing, isn't it? You're using silver not as a mirror, you're using it as a lens to see through. But it works like that on the nanoscale, really weird. And because you can't actually see the image it makes because it's too small, you actually write the image in the photoresist and then you look at the photoresist with an electron microscope. So illuminating with 365 nanometers resolution, they were able to resolve a grating of 60 nanometers period. And that was the first confirmation of optical frequencies, though it had been confirmed that RF frequencies. More visually impactful is the word nano, which was also written in the chromium. And if you don't have any silver there, this is what the word nano looks like. There's a scan across it. It has a half width of 321 nanometers, not surprising given the wavelength. If you put the silver in place, it's like popping your specs on, and the resolution increases by a factor of 6. So these negative things are very, very important for controlling light on the nanoscale. And the reason for that is that if you have a material with a negative epsilon or a negative mu or both, then the surface supports very short wavelength excitation, as known as surface plasmons. And the physical explanation for that is that a metal is thought of as an electron liquid. And like ordinary liquids, the electron liquid has waves on its surface. And these waves are called surface plasmons. They're the analogy of the bulk plasmons. And they can have very, very short wavelengths. And it's resonances in these surface plasmons that give you the effects which create the perfect lens and are the vehicle which we use to control light on the nanoscale. So here's the dispersion of a surface plasmon. Typically the energy here is a few electron volts, so they're in the visible typically. And they typically described by this Drude form of the dielectric function. So below the bulk plasma frequency, epsilon is negative. And when epsilon, if the surface is an interface there, when epsilon is -1, you get this surface plasmon here. And it disperses to longer wavelengths, shorter wave vectors, eventually hitting the light line and coming down here. And it's this property here which we're going to exploit to turn the light into very short wavelength surface plasmons. And then once we've got a very short wavelength, we can push it down to the nanoscale. Now, the first hint that this might be happening was in this experiment here, which is a Raman experiment. In the Raman effect, light hits a molecule, loses a bit of energy to the vibrational motion of the molecule, not very much, and goes off, and hence you can detect the fact that you've excited a vibration. It's a very, very weak effect. And so if you have even quite a strong concentration of molecules at a surface, you shouldn't really see much of a signal for most molecules. But a guy called Fleischmann, who's infamous for other things like cold fusion, yeah. But here's the thing he did which was right, which he discovered this giant Raman resonance. And he found that when he put molecules on his silver surface, that the intensity of the Raman signal was 1,000,000 times stronger than predicted by theory. And the special thing about his surface was it wasn't nice and smooth, it was a rough silver surface. And therefore you could imagine that on the surface there are singularities, and I'll have much to say about them later, where say two particles touch, or you get a sharp cusp or something like that. And it turns out, as I'll show you, that the light is sucked into these singularities and concentrated there into about a square nanometer or maybe less. And so you can imagine that by focusing light in this way, you can get very, very huge enhancements of the local intensity. And so if a molecule is trapped here, then it would have a very strong enhancement, and the light will be enhanced on the way in and it's enhanced on the way out. And so the enhancement is proportional to the 4th power of the field enhancement. So for an enhancement of the field of a factor of 100, you could in principle get 10 to the 8th enhancement of the signal. Now, how do we understand that from the point of view of transformation optics? here I've taken a very, very simple transformation, and I'm going to relate the properties of two cylinders which are touching one another to the properties of a waveguide. So this system is two cylinders, they're touching, and this system consists of two slabs of metal which are separated and just form a waveguide. And I'm going to make a conformal transformation, one that maintains the little angles and so on and so forth. And this, so here's the complex coordinate, x plus iy, x and iy. And I'm just going to do an inversion. And the property of that is if I invert at this point here, points at the origin go to infinity, and points at infinity go to the origin. And in between, these flat surfaces go into the surface of cylinders. Believe me, that's what this particular conformal transformation does. So if you solve the problem in this situation, you can just use the conformal transformation to transform the solution, and that will give you the solution here. And so very, very simply, you can understand this focusing effect. Because, oh, there's one thing I should remind you of, that I said if you do a conformal transformation and this is silver, then this will still be silver also, because you don't change epsilon, you squash and you squash, increase, decrease, decrease, increase, yes. And so this dipole here produces a dipole field, but when you invert about the center, the two charges go to plus or minus infinity, and that creates a uniform electric field, which could be created by some incident electromagnetic radiation. But what this dipole does here is it extracts these surface plasmons, and because this system is a waveguide and translationally invariant, these surface plasmons are just plain waves going off to infinity. Whereas if you then transform them here, infinity has now been squashed to a point here, and so these waves never get to infinity, these waves never get to the focusing point, but they're crushed and go slower and slower, and hence the intense focusing you get here. So you see how useful transformation optics can be to understand these. I mean, if you gave this to a computer, it would have a heart attack because of the singularities here. But transformation optics solves it at one stroke. There's one other amazing thing about it too, and that is something called hidden symmetry. So this system here is translationally invariant. And when a system is translationally invariant, you know what the solutions are. It's not like EPFL. Whereas here, you don't have any such symmetry. Nevertheless, the solutions here are just transformed versions of the solutions here. And so by making the transformations, you've hidden the symmetry, but it's there all the same. It tells you how to classify the waves. That's hugely important in condensed matter theory. In condensed matter theory, if you don't have any symmetry, the system's almost insoluble. I must press on because I have to finish by 2. So if you look at another system here, which you can also get from, which is a crescent, 2 cylinders, one with another, if you like, then this, we calculate the field enhancements here. Here's the field enhancement as a function of angle here. And as you go around to the singular point, you find this massive increase in amplitude here, and also the shortening of the period of the wavelength. I make an analogy with cars on the motorway. So as the cars go slower on the motorway, they obviously get closer together and their density increases, just the same with the photons. It will go on forever, except that you've got some losses in the system, and a very slow moving wave is very susceptible to losses, and the losses eventually kill. But look at this. You get enhancements of about 1,000 here, despite there being losses. So very, very, very effective. Now I'm going to speed on because there's other stuff, but yes, okay, let me come to this one. So here's a system that Fleischmann was working on, and here's just a polished silver surface. And as you know, silver is very reflecting right from the visible into the ultraviolet. So flat silver surface, very reflecting. Silver nanoparticles, you've all seen them. Black and white photographic negative, it's just silver nanoparticles. So by changing the structure, you completely alter the electromagnetic properties of the system. Here's the transmission and reflection coefficient. Metal nanoparticles are some of the darkest material you can make. They call gold blacks and silver blacks. Black, of course, they're black. So just by altering the structure, you get this very strong absorption. I want to show you there's something rather weird about this, and it's related to, yeah. Do any of you talk to string theory? Maybe you've heard of TVs waving their hands about, you know. And one of the things they say, well, sort of, Mr. Physicist, what's your theory about? Oh, well, I work in 12 dimensions. They say, oh, yes, 12. I thought there were only 4. Ah, yes, he said, but the other 8 you can't see. Of course, they're very tiny and they're compacted. Okay. And I've always scratched my head about that and thought, what is compacted? But I believe that these silver nanoparticles are in fact an sort of compacted dimension. So a smooth surface, they're characterized by 2 wave vectors. So if you have light incident on a surface, it's characterized by the 2 angles, the 2 parallel components of the wave vector projected onto the surface. And if you took a compact disk and which is a grating on a surface, and you flash it around, you would actually see that it was colored, and the color would change according to the angle that you looked at it and the angle at which the light was incident on the surface. But if you have a singular surface, they're completely different, and they're characterized by 3 block wave vectors, one of which corresponds to a dimension rolled up into singularity, compacted, and is not conserved, and which enables light to be absorbed across an extensive band of frequencies. So singular surfaces are not colored, they're black. And I believe that's why colloidal silver is black. So very quickly, when I have only a few minutes, let me show you how I can do that with a transformation, a theory of transformation. So here we have a lot of silver slabs piled up periodically and invariant in this direction here. And I'm going to make this transformation here. And what this does is it transforms the x direction into the log of a radius and the y direction into an angle, if this is a complex variable. So, you know, e to the iy makes an angle. And so minus infinity, exponential minus infinity is 0. So minus infinity goes to the origin, and plus infinity, exponential plus infinity is still infinity. And as you go around in angle, dielectric silver, you go dielectric silver, dielectric silver. So that's the first half of the transformation. But we've only squashed the minus infinity direction. So we haven't really got rid of that dimension. So what I'm going to do is to do an inversion about this point here, okay? So points which are close to this point go far away. And points which are a long way from here go to, I got it the wrong way around. Points which are far away come from near the origin. And points which are infinity go to the origin here. So I squash both dimensions, and in between I get an arc of a circle. So I get this lenticular structure. And the third dimension, so this is 3 dimension, 1, 2, and 3 into the blackboard, and the x dimension I've now squashed into these 2 singularities here. And now I'm going to open it up again. So I now do the inverse of this, but now not about this point, I do it about this point. So when we're near the origin, log of 0 is minus infinity, and then I come further up the x-axis here. As I go round, I go through silver, silver, and then I go through silver, dielectric, silver, so I'm coming here, okay. And then when I go beyond this point, the singularities go into these cuffs here. And this surface inherits the 3-dimensional neighbor of this, and the third dimension is compacted into these singularities here. Well, I'm getting on in time, so let me just show you. This is the electric field strength at these singularities in this singular grating here. And something I can also show you is this is another singular structure here, but the singular structure is where the two surfaces touch rather than come into a cusp. Any singularity does the same thing. And as you move towards the singularity here and compress these two surfaces so that this is a methyl, say, and they're touching one another, you see that the spectrum becomes closer and closer and eventually merges into a continuum here. So when next you have your chat with your favorite string theorist, you just tell them, yeah, I heard about that. By the way, have you seen my photographs recently? And with that, I think I'll end. Of course, I'll leave just a second or two for questions. So thank you for your attention.
Very much for making things now. The thing that now is for questions.
Thank you for this fine talk. You said at some point that the negative index line overcome the classic fraction. I wonder how you can elaborate on that, because normally you get a spot that goes to very much positive fraction per stage.
Yes.
And then the average will how do you that again?
So here's the lens. This is maybe the fraction for line lens, if you like. And you have some light here. And the light has two sorts of light. There's the propagating light, and there's the decay light. Okay, and k is equal to the square root of k0 minus k parallel, with the parallel resonant light squared. And as you read that, but if k parallel gets too big, then this quantity k becomes imaginary, and that's what limits the resolution of light. Because k parallel is the Fourier component of the object, and the larger k parallel is the finer detail you can see in that object. And if you try to see something too big, you have ways which instead of going like that, you go like this. And so the challenge of the lens is, if you want to focus something here, the challenge is to take that decaying wave and amplify it so that it comes back to the, and Paul will tell you well how it, so that it comes back to the same value as it was here. Now, how do you amplify something without having any power? And that is the mystery which the lens addresses. And the answer is resonance. So this morning I spent my time with Helmholtz resonators. Thank you very much. And if you work with resonators, what you know is that the classic experiment is the soprano and the wine glass. We've all heard of that. I don't really actually see the soprano singing the wine glass. Anyway, the legend is that if you have a very perfect crystal and a very acoustic cue, and they sing it with the right note, then the resonance will gather the energy of the sound and build it out. It hasn't got an internal source of energy, but it can collect energy from the source, and over time build up a very, very large amplitude. And it's supposed to be make a smash if you have a strong enough singer and fine enough wine glass. And it's the same here. So what this source does is expand the surface resonance, which is these surface platforms I've been talking about, or a generalized surface platform because of the really perfect thing. And that platform, so the matching condition for a platform is that the derivatives of the potential, if you look at the electrostatic approximation, are matched. There are two ways of matching them. There's this way and there's that way. So this solution is a valid solution of the electrostatic equations in that limit. And in general, for the perfect length, it's the solution of Maxwell's equations. And so you can use these resonators to amplify. But of course, the thing about resonators is that they're narrow band. And a perfect length is very, very narrow band. So when you switch on, all you see here is an image with conventional resolution, because those are the only guys who can get through the electricity. But over time, it's like these dedicated that come over the web, you know, first you get a very pixelated thing, and then as you wait, more and more pixels appear. And that's the case here, because you need a very high order resonance to amplify a very high Fourier component. And they're the last ones to come in time. So, yes, I mean, I explained it to you very vividly with all these things, but when you actually look inside it, then you can see. And what happens here is really a mathematical challenge, actually, I should say, that people are not excited about it. Yeah. Any other questions?
Well, I think this all sounds good from a mathematical point of view, okay? But the point is you will be creating a reality, okay?
Yes.
As you well know, the electric function is complex.
Yes.
And the relation between the real part and the imaginary part, okay? This is a fundamental thing. You cannot do anything about it.
Right.
So what are you suggesting to do about to optimize your thing?
Well, Kramers-Kronig, the dispersion relations and so on, they're not such a killer as you might imagine. That's the first thing to express, because what you're referring to is Kramers-Kronig, whereas if you have a certain dispersion in the real part, you're forced to have some loss. But if you recall, that relationship between the real part and the imaginary part is a non-local one. So you can have dispersion at one frequency and absorption at another. And I'd like to point out to people that glass is dispersive, but you can cross the Atlantic in an optical fiber. And the other thing to remark is that the relationship between dispersion of the real part and loss is not between loss, it's between the real and the imaginary part of the refractive index, or of epsilon, if you like. And the other thing I like to point out to people is that there are two materials which have zero loss. One, of course, is with zero imaginary part to epsilon, and the other one with an infinite imaginary part to epsilon. And so very often, or sometimes, a dispersion relationship can be satisfied in a lossless system by having the complement to the real part in an infinitely large imaginary part. So if I take the resonance and have epsilon with this, and if it goes off to infinity, then the imaginary part will be a delta, no loss. So dispersion doesn't necessarily imply loss, but in fractional systems, you are right, loss is a limitation, and the limit to the resolution of these lenses is dictated by how much loss there is in the system. So if we do better than silver, something less lossy than silver, then you could get a more perfect lens, and people have gone down to land upon 20 and so on and so forth. But despite all these limitations, I would remind you of this calculation here, which has the actual epsilon for silver taken from Johnson and Christie, and yet you can focus down this very fine point here. So loss limits things ultimately, but there's a lot you can do even in the presence of Polish loss.
Last question? Thank you very much for the nice talk. I really appreciate your theoretical let's say development, and it seems to be able to describe several interesting properties. But I have more basic questions. Maybe I misunderstood, but so why do you claim that, like for a normal optical systems, you cannot detect objects that are smaller than they are up to the limit?
You mean, why is there an Abbe limit?
No, why? No, I mean, I know the Abbe limit, but why this prevent the detection of objects that are smaller than this?
I'm not talking about the detection of them. I'm talking about resolving them, seeing them. So yes, I mean, if an object is within your field of view, then you can detect it's there, but that's a different matter from actually seeing its detailed geometric shape.
Yeah, so I mean, you can detect like the optical system, like more objects which are like within the Abbe limit. I mean, it's just that I mean, people have detected 5 nanometers quantum dots.
Absolutely, yes,
okay.
Yes, they have, but the efficiency is low because you've got light which is this big, and your quantum dot is yay big, and so you're wasting all this light that doesn't actually hit the quantum dot. And so by focusing the light, you can more efficiently, more reliably expect to have one electron excited for one photon. And that's the point of this very high. So that's why the Raman, in that case, it's a phonon, not an electron being excited. You're coming down to the length scale of the object you want to excite.
All right. So thank you. Thank you. Thank you.